Hello everyone. In this lecture we're going to focus on some selected material from chapter 9 of your text. In this chapter we focus on the topic of knowledge. First we'll discuss the idea of concepts and categories. So first we'll focus on conceptual knowledge. This type of knowledge is the knowledge that enables us to recognize new or novel objects in our environment or events, for example, and to make specifically a concept is some mental representation that we have that we use for a variety of cognitive functions. So, for example, categorization is the process by which things are placed into groups called categories. So this is how we take new objects and place them into some sort of organizational system, and this is something we call categories. And categories are really what make it possible for examples of a particular concept. So why are categories useful for us? Well, they help us understand individual cases that we haven't encountered before. So a new object we've never seen, how do we know what to make of it? How do we know how to label it? Well, this is what categories do for us. They kind of give us what we call pointers to knowledge. So categories provide us with a general kind of bank of information about the item. So it allows us to identify the special characteristics of a specific item as well. So if we use the example of a cat, we can, kind of break down the cat into different characteristics. So we can say they're difficult to train, they have whiskers, they catch mice, they like milk and fish, for example. So this would be different items about cats that would be kind of that information bank that we store about what we know about cats in general. But how do we determine whether or not a new item belongs in a certain category? Well, we determine the category membership of a new item based off of whether or not the new item meets the definition of the category itself. Now, the thing about this is that this doesn't really work very well for us because not all members of everyday categories have the exact same defining features. There's going to be differences between the members. So we use something called family resemblance, and this is a big help to us because basically this is just saying that things in a category will resemble one another in a number of ways, but they're also going to be a bit different. So here, for an example, we're looking at 4 different chairs or pieces of furniture. Now, we would say that these are all items in which we could sit on and technically use as a chair, but if we look at each individual one, they're all very different from one another. They're different colors, they're made of different materials, especially particularly the example in picture D. I mean, that's not even a traditional piece of furniture, that's actually a boy is able to sit in it. So it could also be, just keep in mind that functionality also plays a role in the different ways in which we can define categories. But the idea here is that these all have some sort of family resemblance. These all resemble each other in some way and are functionally or could be functionally similar. Now, one approach we use to categorization is the prototype approach or the typical approach. So basically with this type of approach, we take an average representation of what a typical member of a category would be. And we do this by taking characteristic features that describe what members of that concept are like. So essentially then we average all of the category members that we know of, that we've encountered in the past, together to come up with a composite or an average across all of those different examples. So we have basically a made-up member of that category, which is our prototype for that category. And here in our example below, we would for example, just add up all of these different birds to come up with our prototype bird or our average bird. And that would be what we would use to try to compare new possible members of the category to. So if we are using the prototype approach, we kind of rank all of the members that we. So if we're looking at this line A here above, we can see that the ones that are ranking very high are actually considered to be more poor examples of the category, whereas lower numbers mean that they are a better example of the category. So a sparrow for the category of a bird would be a fairly good example, so it has a lower number rating, whereas a penguin and a bat would be considered to be more poor examples of the category, so they have a higher ranking number. Now, this brings us to this idea of high prototypicality. So, in order to rank these different members of the category, for example, on the spectrum of which ones are better examples or which ones are worse examples of a category, we have this idea of high prototypicality. And this is basically saying that category members that closely resemble the prototype will be considered to be highly prototypical. So we'd say a typical member for the example or category of bird, a robin would be considered to be highly prototypical. Whereas on the opposite end, a low prototypical bird would be considered to be one like a penguin or a bat. So again, this would be a category member that doesn't closely resemble the category prototype. It doesn't mean they're not a member of the category, it just means that they don't closely resemble the prototype or the average of all members of the group. Now, there is a strong positive relationship between prototypicality and family resemblance, as you might imagine. When items have a large amount of overlap with characteristics of other items in the category, the family resemblance of these items is high. So basically, a new item that has a large amount of overlap or similar characteristics to other items that are already in the category, we'd say the family resemblance between the new item and these items are quite high. But if there is very little or low overlap, then there is a lower family resemblance. Now, something called the typicality effect. This is where we see prototypical objects, so items that are highly prototypical of a category. We find that they are processed preferentially, meaning, for an example, that highly prototypical objects are judged more rapidly. So if we look at a sentence verification technique done by Smith and et al. In 74, they basically gave participants a lot of different words, and what they found was that when asked to respond, participants would respond much faster to words that were highly prototypical than words that weren't. So here we're looking at reaction time as a function of amount of prototypicality an object would have, so high, medium, and low. And if we're talking about fruits, for example, apples are very highly prototypical of fruits, whereas pomegranate is not nearly as prototypical. And what we found with reaction time is that participants responded faster to apple than they did to pomegranate. And the idea is that is because apple is more prototypical than pomegranate. So, just in short, prototypical objects are named more rapidly and processed perhaps preferentially. Prototypical category members are more affected by a priming stimulus. So, for example, in this particular study, they primed participants by telling them that they would see green primes, or just priming them with the word green. And basically the idea is that hearing green would prime the highly prototypical green that people have. So here would be an example of that. So mostly our prototypical green would be in this top section here. So this very top bar, we'd see these bright green stimuli. These would be more prototypically green. The one in the middle, they're more poor examples of green. They're very, very faint. And of course in the bottom we have different colors altogether. And we're looking at reaction times between these stimuli. And what they found was that people responded faster to the prototypicality, the highly prototypical green up here, rather than the one in the middle. And again, the idea is that because the participants heard the word green before they saw these stimuli, it kind of primed that prototype that they all had of what green really is. And that is much more consistent with the example B up here rather than C. And that would be the idea as to why people responded to the stimuli B faster than they did to C. Now, in contrast to the prototype approach, there is the exemplar approach. So with this particular approach, we basically say that a concept is represented by multiple examples of different members of the category or concept rather than a single prototype. And examples are actually category members, not averages. So each particular member of a category has its own exemplar, and all of those are used as kind of a basis as to make a judgment as to whether or not a new item is a member of that category or concept or not. So to categorize, basically then you compare the new item to all the stored examples you have of that particular concept, rather than one prototype or average of all existing members. Now this is similar to the prototype view in that it's this idea of representing the category rather than actually defining it. But it's different in that the representation that you have to compare new items to is not abstract. It's not an average of all existing members. You're basically comparing to all existing members. So you have descriptions of specific examples. Now, the more similar to a specific exemplar a new item is, or a specific exemplar is to an unknown category member, the idea with this is that the closer it is to a known family member, the faster it will be categorized. And that's, again, this idea of the family resemblance effect. But remember, with this particular approach, you're basically comparing a new possible member to all known category members. Now, this particular approach, we can say that it explains the typicality effect because it easily takes into account atypical cases. Now, when you're thinking about the category of bird, with the prototype approach, we know that penguin doesn't really compare well to our overall prototype of what a bird is. But if we're comparing new items to individual exemplars, well, then it takes easily into account something like a penguin or a bat, something that doesn't match a prototype because we have an exemplar of that item or that member. And again, this particular approach easily deals with variable categories. So categories that are, it's just essentially highly variable and not very streamlined or consistently easy to categorize new members into. Now, which do we use, prototypes or exemplars? Most people say that we might use both. Essentially that exemplars might work best for small categories, whereas prototypes might work better for larger categories. As you can imagine, if it is a very big category with many, many exemplars, it might not be the easiest thing to do to use that particular approach when there are so many exemplars. It might be better to use the prototype approach in that particular case. But for smaller categories, the exemplar approach might be more beneficial because it might be more accurate because you are actually using real examples of category members. Now we move on to hierarchical organization. So this is basically suggesting that there are three different levels at which we would place items, essentially. So we have a global level, a basic level, and a specific level. So the basic level, as you can see from the figure here, would be things such as car, bicycle, truck, bed, things like that. Global would be more broad or general than that. So car, even more broad than that, would be a vehicle. A bed, even more broad than that, would be a piece of furniture. Now on the specific or subordinate level, these are again more specific than the basic level. So from car, we could say, okay, well, what type of car? Well, is it a Ford, a Chevy, a Hyundai? That would be a specific level. So basically, we organize things based off of these three different levels. Now there is evidence that suggests that there's something very special about the basic level. So if we think about it by looking at this figure here, from the basic level we can either go to the global level in which we lose a lot of information, or we can go to the specific level, but in this case we only gain just a little bit of information. So basically, going above the basic level results in a big loss of information. So if you think about the examples here, going from table to furniture, well, we lose a lot of information there. I mean, furniture is extremely broad. I mean, it could be a bed, or it could be a chair, a table, a footstool, a desk, it could be anything. A table helps us out a lot more. But if we go more specific than the basic level and say it's a kitchen table, well, that helps us out a little bit, but it doesn't give us as much of a gain. So the suggestion is there's something special about the basic level, and for the most part we tend to favor the basic level information because it gives us a good amount of information and it's more useful to us a lot of times when we compare it to the global or specific level. Now, this is all true except when we get to this idea of experts. So, for example, if we look at the naming of birds, for example, if we look at experts, they're using the specific level much more often than our non-experts. Non-experts are using the basic level. So if we show non-experts pictures of birds, they're going to say things like, oh, yeah, that's a bird. But an expert is going to say something like, oh, okay, well, that's a sparrow, or that's a hummingbird. They're going to be a lot more specific. And again, this is just due to a difference in level of knowledge. Okay, so keep in mind that that's something that can affect whether or not somebody is using the basic level or the specific level. All right? Now this kind of brings us to semantic networks, and this is one suggestion of how we take concepts that we have and we arrange them into networks that represent the way concepts are organized in our mind. So you could think about this as being like a huge just basic network of concepts and ideas. So little bubbles connected to one another and branching off of one another, and we'll take a look at how that might look just in a second. This particular idea or model was developed by Collins and Quinlan in '69. And the idea is that for each category or concept that we have, that would be represented in the semantic network by a node. And all concepts are linked. And basically the model is showing how concepts and properties are associated in our mind. So this is an example of how a small amount of a semantic network would look like. So if we're looking at the most general level here of a living thing, well, then we have, along with the actual concept of the idea of a living thing, we have the different things that would constitute a living thing. So can grow, something that breathes, for example. We could list all kinds of things, but basically characteristics about this idea of a living thing. And then branching down from there, we have a plant versus an animal, and then down from there we get more specific. So down from animal, at the very bottom, we have a type of fish. We have a canary and a robin, for example. For a plant, branching down from there, we have a daisy and a rose. And the idea is that everything is connected, but as we get more specific, we branch down. And each node branching off of that will have different characteristics that are associated with that node. So, for example, the node of flower has attached to it leaves and petals, is pretty, things like that that would be associated with the flower. Now, this idea of cognitive economy is highly related to this idea of a semantic network. Now, this is referring to this idea that shared properties are only stored at higher level nodes, not lower level nodes. Now, exceptions to the rule are stored at lower level nodes. So this brings up this idea of inheritance. So lower level items such as canary and robin will automatically share properties from higher level nodes or items such as bird and animal. So even though canary, for example, isn't directly connected with living thing in the network we just looked at, it shares all of those properties because it inherits those properties as we work down the model. Now, exceptions to the rule, again, are stored at lower nodes. And shared properties by multiple nodes are only stored at the higher level, more general nodes. Now, the suggestion with this type of model is that if we're to measure reaction time, items that or characteristics that are more strongly associated with a node are going to be responded to a lot faster than items that are higher up in the hierarchy. So for example, here we're looking at property and category characteristics. And when asked if a canary is a canary, for example, you can see that people responded to that very quickly, because if we think about the idea of a semantic network, the canary is a localization. So it's within that same node. But if we say a canary is a bird, well, it takes a little bit longer for people to respond. And the idea is that they have to travel from the canary node and go up to the higher level node of bird. Now, if we look at property, canary can sing, well, that's something very specific to canaries. But then all the way up to canary has skin. Now, again, the idea there is, again, the person is having to kind of work backward and go to the higher level node. And that's what's resulting in this higher response time overall to these statements. Now, as you might imagine, the semantic network kind of has this idea attached to it of spreading activation. So activation is basically the arousal level of a node. So how much a node is being activated, essentially. So when a node is activated, this activity spreads out along all the connected links to that node. And concepts that receive activation are essentially primed and more easily accessed by memory. Now, there is a kind of a contrasting idea to semantic networks, and this is the connectionist approach. This particular idea was really created based off of computer modeling. So using the idea of computer models for representing our cognitive processes. The idea with this type of approach is that we do parallel distributed processing, meaning that we process several things in parallel. And basically, with this approach, knowledge would be represented in the model in the distributed activity of many units, rather than one unit linked to the next, to the next, to the next. And there are weights associated with each unit within this particular approach. And these weights are determined at each connection in terms of how strongly an incoming signal will activate the next unit. So the connectionist approach looks something like this. We have output units connected to hidden units connected to input units. So the first thing that we have would be our input units. So this is what is receiving stimulation from the environment. So these are activated by things that are incoming from our environment. These then move on to hidden units. So their responsibility is to receive input from our input units, and then finally moving along to output units. So this is what's receiving the input from hidden units. So we go from input units to hidden units and finally output units. So here in this figure we take a look at a very small example of a connectionist network. Now keep in mind that the proposal for how a connectionist network would actually look, it would be much more vast than this, much larger. This would be just a very, very, very small segment. But here the idea is, for example, the word, if we look under concept here, the word canary would be activated. And then this leads to activation of lots of other units throughout the system. And so this moves along to hidden units, and then finally we lead to the activation of things such as grow, move, fly, and sing, basically characteristics or properties that a canary has. So this is just a very small example of how this particular system tries to explain how all these ideas and characteristics about a concept are activated. Now, according to this approach, learning occurs when the network responds to a stimulus and is essentially provided with the correct response. And over experience or just times of exposure, modifies responding in such a way to match the correct response that's needed. Now, in order to modify responses over repeated exposures to eventually get to the correct response, there has to be some sort of an error signal. So basically the error signal that is received into the system is the difference between the actual activity that's occurring of each output unit and the correct activity that's actually needed. And basically the error signal is transmitted back through the circuit itself, and this is called back propagation. Now, basically what this tells the system is how the weights on each unit should be changed to allow the output signal to match the correct signal that's desired. And this process essentially repeats itself until the error signal is gone or is zero. Now, something that can happen according to the connectionist approach is something called graceful degradation. And this is something that happens when there's some disruption in performance, and this occurs gradually as parts of the system itself are actually damaged. Now, for this particular chapter, make sure to take a look at the connectionist approach, which we've been going through. And again, this is basically modeled a lot more off of a computer model versus the semantic network approach. Make sure you understand the different approaches and the ideas that each of them are suggesting and what each approach would predict in terms of how categorization and conceptualization would work. Now moving on to categories of the brain. We do have some data that suggests that different areas of our brain might be specialized to process information about different categories. So essentially, we might have some evidence for a double dissociation for categories of living things versus non-living things, for example. And this would really give us some support for this idea of category-specific memory impairment, meaning that you could have an impairment that would be only affecting you for a very specific category. Now here we have data from patient KC and patient EW, and what we're seeing here is that if we're looking at percent correct performance, both patients aren't doing very well with identifying or correctly naming living animals, pictures with living animals, but they're doing much better with non-animals. So pictures with things such as fruits, vegetables, furniture, things like that. They're doing much better with that than they are actual living animals. So this is giving some sort of supportive evidence that there might be some sort of category-specific impairment that is possible to have. And this also tells us then that perhaps different categories might be activated in different areas of the brain. So as always, make sure to check through this chapter very carefully, and please enjoy reading this week, and I'll be back with you next week.